During the webinar, if you have any questions, please ask them through the questions box in GoToWebinar, and we will answer as many as we can during the last few minutes of the webinar. Also, we will have 2 poll questions. So whenever a poll question pops up, you can just go to the link that will be shown on the slide, and I will also send it out on the chat box to everyone, and just choose your answer, and so we'll see what you respond. Now to start our first poll question, I just sent out the link where you can go and vote. So the question is, have you heard of or used the iBwave Wi-Fi tool? You can make your selection now, and that will just give us an idea of what your knowledge is about iBwave. We already see some responses coming in. We'll wait a few more seconds. Okay, so seems like most of you have heard of it but not used it. And some of you have not heard of it before, so today is a good opportunity to get introduced to the various functionalities of what the iBwave Wi-Fi can do. Just a quick overview of who we are in case you don't know us. We are iBwave. We're the standard for in-building wireless design. We've been there for over 13 years. And we are the worldwide standard, trusted by over 900 customers in more than 90 countries. So we're available worldwide, and we offer a complete suite of solutions for all technologies, including DAS, cellular, and Wi-Fi. And we are continuously innovating to bring you the latest solutions for in-building design. Now I will ask Vladan to get us started on the actual presentation.
Hello everybody, thank you Anna for the introduction. My name is Vladan Jevremovic. I'm a research director at iBwave, and as such I am responsible for improving our offerings from the point of view of accuracy, and including new features and new standardizations. Today we will talk about 802.11. Specifically we will talk about capacity in 802.11, and we will focus on factors affecting capacity dimensioning, how granularity affects capacity dimensioning, and then how the presence of cellular is going to affect Wi-Fi. And then we will close our presentation with a demo for the last 15 to 20 minutes. First on the agenda is factors affecting capacity dimensioning. We will cover quality of service, type of the venue, the number of client streams, user density, 802.11 overhead, ambient noise, and available airtime. So let's get started. First is quality of service of applications running. There are 4 QoS types in 802.11: voice, video, best effort, and the background. And what's important is that voice and video are less packet jitter and packet delay tolerant than file transfer. What it means is that if you have a venue where predominant use case is voice over IP, it means that you need more APs than for a venue where the predominant use may be file transfer. The reason being is that you basically are going to have to be able to execute the roaming much faster, and to do that you need more APs per square meter. So that affects the density of APs, the count of APs, and that's why you have to be aware of the quality of service of the applications that are going to be predominant use in that particular venue. Also, the venue type may dictate what kind of applications are going to be used. In retail, we have mostly low data rate applications, which we are basically scanning for articles, and that really is a very low data rate application. On the other hand, what we have is stadiums that are very data intensive. It is largely file transfer in both directions. So because of that, because you need a higher data rate, your SNR has to be higher because your maximum achievable data rate and data throughput per APs has to be higher in order to support large file transfer. So that venue type would obviously need a denser APs than retail. On the other hand, we have hospital, where voice is one of the predominant applications, and we have just said that voice has a different QoS type than file transfer. So we need even denser count of APs there. And there's also real-time location services in a hospital. So as you see, venue type is going to dictate the application, and applications themselves may have a different QoS. So those are the factors that will affect your KPIs, and consequently, it will affect your AP count. Then the next one is the number of streams per client. You probably would hear things such as 8.11 AC Wave 2 will have 4x4 MIMO. That is true, but having 4x4 MIMO in a standard does not mean that all your clients will be capable of streaming 4 streams. As a matter of fact, the number of streams affects battery life. And as you know, it is not the same if you are using a laptop versus iPad versus smartphone. The difference being that the laptop is going to be plugged into AC power most of the time, and as such can easily support three streams or even 4 streams. On the other hand, as your smartphone is mostly running on battery, so having 4 streams, meaning basically having 4 transmitters and receivers in your 8.11 chipset, would drain battery much faster than having 2 or 1. And that is why most of the time your smartphone will have a single stream, even though it is capable of running 8.11 AC stream wave number 2. So what it means is that your smartphone is not going to have the same data throughput than your laptop. Your laptop is going to be much faster in that respect, running higher data rates than your smartphone, because your laptop has 4 streams and your smartphone may only have 1. And tablets may have only 2 streams, because tablets sometimes are running on AC and sometimes on battery. Then we have user density. In general, in manufacturing, user density is low. We just said that it is mostly scanning of articles in manufacturing. And then there are more users in an office environment when they're mostly sitting by the desk and running applications from their laptop. And then there's even more users in a hospital. That's a denser environment than office. And then we have ultra-dense venues, such as stadiums, where we have may have a few tens of thousands of users, maybe even up to 100,000 users at an event. So as you see, the venue type, venue vertical, not only affects the applications, it affects the user density. And the mere fact that a battery life is limited is going to dictate how many streams you may have on your client. The next topic is 8.11 technology, namely technology overhead. As you may know, 8.11 A, B, and G, those older technologies, they have quite a bit of overhead due to the collision avoidance algorithm, the way it is implemented. there basically every frame needs to be acknowledged, and then there is a contention period there. So the problem there is that there is quite a bit of time when nobody is transmitting, and that is by design to increase the odds that nobody is going to collide, basically to minimize the collision, to minimize on-air collision. So if your 802.11a device is rated at 54 megabits per second, which is the maximum achievable data rate in the technology, that is your layer 1 data rate. When you take into account the mechanism that happens at layer 2, which is for the collision avoidance, then only about half of that maximum achievable data rate is actually available for throughput. So your 802.11a device actually has a throughput of 27 megabits per second, not 54 megabits per second. At the later technologies, 802.11n and AC, this is actually a bit better. There, the actual throughput is 80% of the listed maximum data rate because of the mechanism that allow you to acknowledge a group of packets that is sent at the same time. So you're only acknowledging at the end. That actually reduces the airtime where nobody is talking, and that's why the throughput is higher, actually closer to the maximum achievable data rate that you see listed in the PR material. Then there is ambient or background noise, and this is actually the result of the fact that unlicensed spectrum has other things transmitting than just 802.11 transmitters. And because there are a lot of them transmitting, they may end up being below the trigger level at the receiver, at the 802.11 receiver. But even though they're below the trigger level, their signal is being added at the receiver, and receiver recognizes that signal as a noise. So you may have a rather large, rather high noise level in some of the venues. And if that is the case, then you are going to be using a different KPI of choice when designing the network. What I mean by that is if the noise level is comparatively low, let's say neg 90 dBm or less, then you are going to use a signal level as your KPI. But if it is higher than neg 90 dBm, then you are going to use signal to noise ratio as your KPI target. And at some venues, the background noise is well above neg 90 dBm. And then there is available airtime. So why do we have that? Well, we don't really want to design for 100% available airtime. If you do that, then we will have an AP that is busy all the time, and nobody is going to be able to get in until somebody gets out. And that is not really very useful when you are designing the network for your busiest time. If you design the network to be 100% available airtime during your busy hour, during the busy hour, you will have a problem people actually getting in. And so that's why you would want to have your target available airtime to be lower than 100%. Typical value is 80%, and it can be a bit lower than that depending on the environment. So what is RF propagation granularity? This we have a granularity in 2D and 3D, and I'm going to explain what I mean by 2D on this slide. This is a floor plan of a hotel that actually has, as you see, the guest rooms at the perimeter, and then there are areas with a pool in the middle, and that area is open area. And then there is a semi-open area where conference rooms are. So the RF propagation environment is different in the areas where there are guest rooms versus open area versus semi-open area. So what I'm trying to say is that trying to use Excel spreadsheet to calculate the RF path loss in a venue like this, which is not homogeneous, is going to be futile, because you would have to use 3 different spreadsheets for 3 different areas that I have identified. And on top of it, there is an area with inclined surface. This is not a topic that we will cover much, but let's just say that inclined surface is very different than what you would see in the horizontal surfaces. So basically what I'm trying to say here is that using the spreadsheet is very limited in its usefulness, and I am showing an example where due to the very different RF environments, a spreadsheet would not be very useful in this case. And then there is 3-dimensional granularity. What I have shown you in a previous slide was just what's happening on the first floor. On the second floor, I don't have conference rooms, I don't have the swimming pool, I only have guest rooms. So on the second floor, I'm going to have to use just a portion of the RF environments that I have listed. And so this is the case with the third floor as well. But keep in mind that transmitters on the second and the third floor affect the RF signal on the first floor as well, because we cannot contain signals perfectly on the second and third floor, especially when we have an open atrium like we have in here. So whatever I put on the second and third floor will have a signal that is going to be, be noticeable, at least in this area. So when I do the propagation calculation, path loss calculation, I have to account for transmitters not only on the same floor, but on the floors above. So what does it really mean? Well, here's an example of what happens with the CCI calculation. CCI heat map is shown on this slide, both on the left and the right-hand side. But the left-hand side is what's happening when I'm taking into account only transmitters on the same floor. You see that CCI is not very good here. I have a CCI equal to 3 in most of this open area, but that's the topic that we will talk about a little bit later. But this is 2D CCI prediction, 2D CCI heat map. 3D CCI prediction takes into account transmitters on the second and third floor, and it is much messier. You see, while CCI equal to 3 was recorded on the 2D prediction, on 3D prediction I go all the way up to 10. There isn't that much area with CCI equal to 10. Mostly, you have less than that. But the mere fact that you go from 3 to 10 shows you how important it is to take into account what's happening on the floors above you. If you have, especially if you have a situation where there is an atrium where the signal can be noticeable from the transmitters that are on the second and the third floor. So this is why our propagation granularity has to be taken into account, namely why doing a 3D prediction is very, very important if you want to get an accurate calculation of your CCI heat map. And as you may know, CCI heat map is really critical for your throughput. So user profile granularity is the next topic, and that is to say that most clients run a variety of applications over a period of time. It is important to specify the period of activity that we think will be the time when most of the traffic would occur, which we colloquially call a busy hour, and the applications that are likely to be used. And not only the applications, but the quantity of those applications that will be used. Basically, we need to specify, the files in megabytes. And why is that? Because what we really want to be able to say is an average user is transmitting 100 megabytes over a busy hour, or 2 hours, or 3 hours, whatever the time period is. So we decided to use megabytes as the capacity calculation KPI, is because that is essentially what you will see in your monthly usage. You will basically say, I have used 5 gigabytes of data, or 10 gigabytes of data, or 100 gigabytes of data over the past month. You can do the same thing if you are trying to predict what is going on to happen over a busy hour at a venue. Only your units are going to be slightly different. It's going to be megabytes most likely. So these specifications are often referred as user profile. I'm basically trying to say what an average user in a hospital or in a stadium or in some other venue is going to spend when it comes to the file size, or transmit, if you will, as far as file size during busy hour. So that is to say that the different verticals, and I just mentioned stadium and a hospital, may have different needs when it comes to transferring files. So it is important to understand that a user profile is different for different verticals. And then we have just explained that we have a different user profile for each venue. Then within each venue, we may have areas that are called capacity zones, where users may actually transmit more than for the rest of the venue, more or less, as a matter of fact. But typically, it is more. And in this example, a hotel has different client density in hotel rooms, different conference rooms, and different at the reception and desk breakfast area. A different number of clients will be present in those areas. And they also may have different usage patterns, because in a conference room, a client may just download mail and browse web pages, whereas in hotel room, a client may run mostly videos, standard definition and high definition videos. And then at the reception desk, it will be back to just web browsing. So this needs to be recognized, and then because it is important to do this, because we are recognizing the fact that we have non-uniform distribution of clients and non-uniform distribution of user profiles within each venue. So that allows us greater granularity for each venue and greater precision calculating our capacity. Lastly, we need to touch on the subject of cellular and Wi-Fi, because a lot of venues have a mix of a small cell or DAS and access points. Some cellular carriers offload their traffic to partner Wi-Fi providers, and that offloading mechanism may vary. Offload would be by application type. It could be voice versus video versus data. Some operators like to offload voice if they can. Then there's offload, and some like to offload videos or data to Wi-Fi. Then there would be offload by signal KPI threshold, meaning if my signal or my signal-to-noise ratio goes below a certain KPI, then I'm going to offload to Wi-Fi network. And then there may be offload by cell load threshold, which means that if my cell site is getting a lot of traffic, then I'm going to offload to Wi-Fi. Regardless of that, even if you are in a venue that only has that does not have a small cell or DAS, even if you are in a venue where you are designing for Wi-Fi only, you need to recognize that some customers are not going to get on a Wi-Fi network for whatever reason. And especially is true if, for example, in this hotel, in the reception desk area, you're going to have a client that's coming in, and maybe there is a line for check-in, and the user wants to browse the network. He still does not have a username and password, so he would use cellular network. And some would decide to use cellular network maybe in conference rooms, in hotel rooms, and so on and so forth. So we need to specify the percentage of the users that will go cellular all the time in each of those capacity zones and in each floor of the venue. It is maybe not be a significant percentage, but to be able to precisely calculate the capacity, we need to pay attention to that as well. So what do we have? We have a solution, iBwave Suite, and this actually is of what we have is called iBwave Mobile, iBwave Wi-Fi, and iBwave Unity. So this is basically three-pronged solution that we have for your Wi-Fi needs, and we also have a very large database of hardware that is used in the design, and we also offer training and certification. So what can that solution package offer do for you? It can accelerate your Wi-Fi deployments by 50%. It can ensure that you are designing carrier-grade Wi-Fi network, and it can reduce project costs by 30%. As I mentioned, we have full database of over 25,000 parts. You can collaborate easily with your project partners because we offer iBwave Unity, which is our server through which you can exchange files. And you can thus manage all your projects from a central hub. Namely, if you are going out there and doing the site survey, you can use iBwave Mobile, and then you are taking pictures, taking notes, maybe doing the initial design and uploading that on a server, whereas at a central location you may have a person whose only job is to download those files, and then based on your survey notes and pictures, you will finalize the design using iBwave Wi-Fi on a PC. And then we're going to go through a demo. Before we start, I'm just going to give you an example of what are we going to have. It is a 3-level Holiday Inn with open pool, and this is a 3D view of the venue with just walls. We have an option to show you the same venue using wireframe, and then the question is, why would you want to have a wireframe? If you have a wireframe, this will allows you to actually peek, what is happening behind the walls, and this is useful when you actually put your APs, so you can see them in a 3-dimensional view, and then you can also see the equipment that you have designed using this wireframe view. And then when it comes to the heat maps, you can see the layered heat maps in the 3D view. This one is signal level, and this one is actually average downlink data rate. This is something that I will be touching upon a little bit later on when I show you the example in the map. But let's now move on to our demo. The first thing that I want to show you is what exactly we can do, and in our software, how we go about capacity. So for the capacity, what we do in the requirements area, we are defining clients per floor and clients per capacity zone. In this example, we have 3 floor levels, and for each we define the number of subscribers per floor, and this is basically the number of clients in peak time. And then there is a usage profile. I told you that subscriber profiles or usage profile that we have, we use that term interchangeably. It means the same thing. There is a user profile defined for a hotel. I'm going to show you what it is in a few minutes, but here is where we actually have an option of actually assigning different user profile for different floors if we want. In this example, it is a user profile for hotel, but we have others as well. And then so we decided to assign user profile hotel for all 3 hotel floors. And then there is what I have explained earlier, you are going to always have some people that will stay on cellular. So we have put 10%, we estimated that 10% of the clients will always be cellular and Wi-Fi will be 90% for each floor. And then we go into greater granularity. As I explained earlier, there are some areas here, and I'm going to remove signal strength so I can point them out. Here is a pool area that I talked about, and there are conference rooms. There are 2 of them. And then this is a lobby area as well. So I have defined the number of users per floor, and then I'm now recognizing the area that are, a little bit, they have a different density. So there, what I'm going to do is I'm going to go and say I have capacity zones on the floor number 1, and they are 2 conference rooms called Galleria and Encantada, and then there is a lobby, and then there is pool. And for each of them, I'm going to define the number of clients, and those are in addition to what I have defined in the clients per floor. And then I'm going to assign usage profile. Conference rooms for conference rooms. Lobby, I assign the same user profile as for the hotel, and then there is a conference room profile at the pool. And then I'm also going to assign percentage of cellular versus Wi-Fi. And see, if you recall, I said that in a lobby you are going to have a larger percentage of clients being on cellular than on, and so this is reflected in here. I have 50% of them being on cellular network because most of them have not gotten their username yet. So that is the first step. The next step is to go and figure out the market share, and this for Y and split by client type. As I said earlier, client type, some clients will have higher order MIMO 3x3 or 4x4, and they are mostly laptops. And then I'm going to have clients which are mostly smartphones that will have a single UE, which we call SISO, a single stream, which we call SISO, and then there's going to be clients with 2 streams, mostly tablets. So I need to have a breakdown percentage-wise between those 3 types. And then the APs are going to be dual band in this example, so I need to make some assumption as to what the breakdown between the clients would be. Now you're going to look at this and think, well, why would you put 80% of your clients at 2.4? That doesn't make sense. Well, I'm doing this to illustrate my point in the design. So we will get to it in a few minutes. Then finally, I'm going to go and spend some time about the user profiles. I have listed the default user profiles there. And those were done just to illustrate the point that we are going to have a different amount of files that are going to be transmitted at different venues. For example, you will see that at hotel and at the airport, I have a much different file size than what I'm going to have at, let's say, shopping mall. And University of Campus is by far the heaviest. So this reflects, the fact that you have to pay attention to the request for the different file size that is typically being transferred to those venues. But if you want to create your own venue, you can do that by by pressing the plus sign, and then you can say things such as new venue, and then what you can do there is you can actually increase the file size. You do that by increasing the estimated amounts of usage of each of those applications. For example, I have 10-page web browsing. If I decide that I'm going to have more, then it is 50, and now you see the file size has increased a little bit if you want to stream music more, it is going to show immediately in the total file size there as well. And video streaming as well, is going to affect quite a bit. Then also you can define a custom-made period. Doesn't have to be 2 hours, which was in this default case. It can be 1 hour, and you see it is going to change your required throughput as well. When we talk about throughput, in this context, you have to realize that this is a throughput, average throughput per period of time. This is 1 hour, so you have your average throughput, and it will change if you go to 3 hours. It will be about 1/3 of it was originally there. So what you have there is your throughput defined over a period of time. So this is roughly 1 megabits per second over 1 hour. Okay, so it is not instantaneous throughput. It is much higher than that. But when you average out over the full hour, it gets much lower. So we have that. And then the last one is subscriber service. And there what we have done is we have defined the default file size for each of those services. And also we have defined the default average data rate for the streaming services. And the purpose for that was basically to help us with those values that we have in our values. There we have the estimated, which is unit size. So we have 6 units, and then we have the total amount in megabytes, 6 times the default unit size, which we get from here. So this is something that you will not use. Very often what you will use instead is these values and the values that are in there, and to know how to increase them is just to increase the incremental size here, going from 10 to 50, which is going to increase the size of files here, which is we just showed you. So that's that, and then I want to show you the design that I have here, and how to recognize a bad design and what to do about it. So this is a default design that I have, and what you will notice, there is an AP in the middle of the open area, and that AP is transmitting at the full power, which is 20 dBm. And by the way, I have used generic AP just to be neutral in my analysis. So I'm having an AP that is in the middle of open area, transmitting at 20 dBm. Not only that, but I have all other APs that are transmitting at 20 dBm throughout. Okay, so this that comes straight out of box. It's 20 dBm. You see, I have areas that are semi-open or open, and they're all transmitting at the high power. As a result, I have a very hot heat map that shows what is going on the first floor. And you may think this looks really great, but as I have said earlier, the co-channel interference is kind of bad in here. And I'm going to stop for a second and address the fact that I did say that we need to have a 3-dimensional view of CCI, and I did show you exactly this heat map and told you this is 2-dimensional, and that we should not take into account 2-dimensional heat maps, that we need to have 3-dimensional view of what is going on. So having said that, I limited the analysis on this floor only because I'm going to run a live example in a few minutes, and because there are so many transmitters, it takes a little bit of time. It takes a few minutes to do this. And as we have a limited time in this webinar, it is to our advantage to speed things up. And that's the reason why I'm showing you 2D CCI as opposed to 3D CCI. So having said that, then running the capacity analysis, and these are the things that I have done in the background before this webinar. What you have is a capacity map, and our capacity map can show you each AP in 3 different states. It can be either pass or fail, or fail due to the air interface and fail due to the equipment. So what does it mean? If it fails with the equipment, it is because it has too many connections. As you can see here, for each of those, you can define the maximum number of connected clients. And in this example, this says it is 64. So if I calculate my capacity map, it will calculate the number of simultaneous connections for each of those APs. And if it is larger than 64, then I'm failing. So I'm going to show you how that looks like. You see the second line, it says traffic and number of clients. The first number is the number in the area. So this particular AP, AP number 6, actually has 2 different areas it is covering. One area is capacity zone, and then the other area is the rest. So that's why you have 2 numbers. The first number is the number in clients in capacity zone, and the second number is the total number of the clients that it covers in the whole area that this AP number 6 is dominant. So the second number is important when we figure out whether we have too many connections. So the second number is 93, and the limit is 64, and that is why we are failing. So this one is failing due to the too many connections. But it can fail also if the airtime is greater than the specified number. In our examples, the specified airtime is 80%. So each AP has to have airtime equal to or less than 80%. And here in this example, you see airtime utilization is 154%. We have specified 80%. And 80%, and that is much more than what we were hoping. I'm now going to stop and use a different source for voice because I'm telling you.
Vladan, I'm sorry to disturb, but the audio quality on your side is breaking up. Can you please check?
Hello, I'm back. Hopefully this is better. Anna told me that we had difficulties with the phone connection. So I'm going to repeat what I was saying here for the last few minutes. When failing, AP can fail in 2 ways. It can fail due to the too many connections, which is equipment fail, and it can fail due to the airtime percentage being higher than specified. If you recall, in properties, when we were basically saying what the market share is, we specify airtime utilization. So in this example, airtime utilization has to be less than 80%. So here you see I have a situation where my airtime utilization is 154% for AP number 7. And that is much greater than 80%, so this guy is failing due to the physical layer limitations. For this particular AP, the number of clients is less than 64, and that is why he has not failed that requirement. If AP is passing, like AP number 8 is, then both of those are conditions are satisfied. The airtime utilization here is about 37%, which is much less than 80%, and the number of clients for this AP is 21. So this is example what you will get if you would try to do the client heat map based on the default design, which gives you this. And as I said, we know this is not good, so the question is, what do we do first? Well, first we try to reduce co-channel interference, which is how it looks like originally. So I did that, and I'm going to show you the second map. And in the second map, what I did is first I have reduced the transmit power. Well, first of all, I have removed this AP that was in the center of the area right next to the pool. I moved it to the side, and there it is. And also I also have reduced its transmit power. So now it's at meg 5 dBm. Not only that, I have reduced the transmit power for others. This one is from 20 to 0 dBm, and these two are also not transmitting at the full power at 0 dBm. This one. And so when I do that, I now have to take a look and see what is my signal strength. What does it do? Well, okay, so you are now going to see that you're not as hot as you were at the time, and then you see what your power levels look like right here. And as you see, not all of those are transmitting, namely this one is not transmitting, this one is not transmitting, and if you're not satisfied with this, you can turn them on. But the reason why some are not transmitting, this is at 2.4. And not all transmitters are needed at 2.4, but are needed at 5. So that's why you have some that are not transmitting at 2.4. These would be transmitting at 5. So if this is acceptable, then you run co-channel interference, and then you see that you have eliminated a CCI equal to 3. So you only have 0, 1, and 2, which is better. And then the question is, what is going to happen with the capacity? I did run, again, in the background, the capacity analysis, and it is better. It is better than it used to be. You see, it used to be that I had all this area red. I'm going to remind you by going in here. All this was red, and now it is a bit better, okay? But it's still not where we want to be. So the question is, what is the problem? Well, you may remember that I told you at the beginning that I did something that should not be done usually, which is the breakdown of between 2.4 and 5 gig. I have 75% at 2.4 and 25% at 5 gig. So this is obviously not something that you want. So let's try to see what is going to happen if I do it the other way around. So I'm going to go there and I'm going to rerun capacity. So I'm now doing the analysis only on this floor, so that's why it's so fast. So yes, obviously I'm better now. I'm not failing at 2.4. The question is, am I okay at in here at 5? So now I'm running at 5. I have more APs on 5 because all of them are now transmitting, whereas about half of them are transmitting at 2.4. So this analysis is going to take longer. And as you see, I'm only running them on this floor. If I were to run throughout the whole building, it will be much longer. And for the sake of timekeeping, we are doing it on 2D only. So as you see, when it's running capacity analysis, it first calculates maximum achievable data rate and then calculates capacity, and it's now completed. It took about 2.5 minutes, and as you see, it is passing at both 2.4 and 5. So this is our this concludes our presentation, our demo, and now we are going to go back to the slides. We are now going to go through another poll. So Amna, please take over.
Thank you, Vladan. So as you can see, the poll question, this question is, which one of the following would you say is the most common problem you have on your WLAN? To respond, you can go to pollev.com/ibw. I texted it out at the beginning, and you can also see it right on the slide. So just go to this link and make your selection. I'll give you a few minutes to vote. Response is coming in. If you haven't voted, you can go to pollev.com/ibw. We'll just wait for a few more seconds. Okay, sounds like we have the result. The first one is clients unable to connect. 75% of you think that's the most common problem. Wait, it's still moving, so now it's 67, and then at number 2 is older clients slowing everything down, and then the last choice for 10% is insufficient throughput for clients. Okay, thank you for your participation, everyone.
Okay, I will just want to make a few comments here, namely, clients unable to connect, it can be tied to capacity problem. As we have said in our demo, the failure to connect, it may be due to the too many clients connected already at a particular AP. Older clients slowing everything down is something that you will have to deal with because legacy systems B and G, there is a protection mechanism that exists there that when B and G client connects to a network, and that indeed does slow everything down. As for insufficient throughput for clients, I want to point out that we do have a feature in our tool that is average downlink data rate, which is per client, which is a map that will show you what is the data rate per client throughout the venue, which can be quite useful in the context of you examining what exactly is why do you have a problem with the throughput. So that concludes my end of presentation, and I'm now turning this over to Anna to wrap up the webinar.
Thanks, Vladan. We are running out of time, but we'll take a few questions. We already have some come in, but if you still have questions, feel free to use the chat box to send them our way. So Vladan, the first question is, what are the different propagation models that are available in iBwave Wi-Fi?
Okay, We are going to, this is a topic that we're going to address in another webinar, but we have COST 231, which is very well known direct path propagation algorithm, and then we have something that we have developed ourselves, which is fast ray tracing, which is basically a variant on ray tracing algorithm that takes into account reflection, diffraction, and direct path. It takes many paths between transmitter and receiver that are bouncing off objects, walls, or diffracting from walls, or penetrating through the walls. So those are two main algorithms that exist in our tool.
Thank you. So another question is, does iBwave Wi-Fi have the same capabilities as Wi-Fi, the regular iBwave tool?
Yes, it does. What we have done is we have stripped down the other technologies, and now we have only Wi-Fi at 2.4 and 5 gigahertz. We did that to reduce the cost, to reduce the price of our offering. So basically, Wi-Fi tool, iBwave Wi-Fi, is for Wi-Fi and Wi-Fi only. So you can only analyze Wi-Fi, but you still have all the other functionalities that exist in iBwave design.
Thank you. So there's another question. Does iBwave manage co-channel Wi-Fi networks?
Does Wi-Fi manage co-channel Wi-Fi networks? Yes, but what I would imagine is if you can actually go in and take into account the other Wi-Fi networks that exist that are not the Wi-Fi network that you design. Yes, you can actually import the survey data that you have that will be from the existing Wi-Fi networks, and you take that into account when you are doing the design.
Okay, so let's just do one last question. Can you define your own usage profiles, or are they hard-coded and you have to use a built-in profile?
Yes, you can. Here it is, and you go back to the project properties and their usage profile. You click on plus, and that's the usage profile that you can define yourself. It doesn't have to be what we have defined. So you have that option.
Thank you, Vladan. I'm going to wrap up the webinar. I would like to thank everyone for attending and apologize for the brief audio difficulties that you experienced. We will send out the recording of the slides shortly, and I have sent out a link for an available free 15-day trial of our Wi-Fi tool to our website. So if you would like to sign up and try it out, please feel free to do so. Once again, thank you everyone for attending, and have a nice day.
Bye-bye.